That's how you capture the proportions in the probabilities. Okay. So my question is that there are Markov models where you use rates also, right? So if you are given a data on proportions and you want to convert into rate, what do? You leave the problem. Any idea? It's a very simple thing I am asking. You see how tricky it is? As soon as I start asking this thing, that is what she is talking about on the slides. I'm not sure if we understood what she was mentioning. So there is a simple model is used to convert proportion to rates and vice versa. Right? So it's you take a box and you put an arrow out of the box. And let's say I represent the things in the box is X and the arrow coming out is a rate, let's say gamma. So you have X prime, the change. So this thing is leaking out. Suppose there is a tap, it's leaking out the water and there is a water fill there. And you want to know how is X changing. So the leaking out is X prime is equal to minus gamma X, right? It's a linear equation, you can solve it. Once you solve it, you will guess X, right? You will get xt equal to, it will be an exponential solution by the way, right? So then what you do, this is xt, right? At time t, if it is leaking out every time. Then you started with x0, right? You started with x0, initial amount of the container, x. So you subtract x0 minus xt, that's what is left right now. Does that make sense? And you divide it by x0, that's a proportion. Is that making sense? At time t, you are getting proportion by taking x0 minus xt divided by x0. And the right hand side will be the rate in exponential form. Although I am just giving it in words, I can write it down if there is a board, but it's very, very simple, but proportion is used. So then as soon as you write x0 minus xt divided by x0, that's a proportion. And the right side is a gamma, which is a rate. So now you have a proportion of people in the compartment and the rate at which it is leaking out. So you can convert this, use this formula. You can isolate rate if you are interested in finding rate from given the proportion, or you can have a proportion in the terms of the rate. Now it's an approximation, it's not an exact answer, but this happens all the time. Simple things, and we struggle days, months of finding these estimates. So that is what she is trying to explain. There are subtle things, very subtle. She's talking about uncertainties, right? Where is the uncertainty come from? You know, I will be talking about stochastic frameworks in the very end. These are advanced models. But when we say stochasticity, what does that mean? Statistician spends whole their life evaluating uncertainty. That's their bread and butter. That's their roots analysis research. They only look at the uncertainty. So she is telling very important things in each and every sentence if you carefully listen what she's saying. Which is not obvious to a mathematician or non-statistician, I would say. Not obvious. You learn it by, people in statistics have spent they have done the degree as well, just like us did in mathematics or anthropology or biomedical sciences. We did it in our own field, right? It's a different language. So uncertainty, can you tell what is the uncertainty means? What does uncertainty means when it comes to your mind?
Not like randomness in any process.
But where is it coming from? That's my question.
Like in epidemiology, mathematicians use continuous model with differential equations. They do some assumptions.
Again, you are going to the methods. Just give me where is the uncertainty coming from? My simple question.
Yeah, like
But why? Why is coming from data? If that is coming from data, and that
Like
is
in-
not the only uncertainty.
Like in data, if some epidemiological survey is done in some hospital, sometimes they are asking for age. So some people don't mention their age, sometimes they don't mention their gender. That's
Okay, well that's a missing data, but that's not an uncertainty.
Incomplete information.
like this, a person is infected, he meets many susceptible ones. Now it is uncertain whether he is meeting 4 guys who is getting infection and who is not getting infection. This is not
So what you are saying is a human error. Human error?
Sir, one is infected and I am infected from a disease. I am meeting 4 susceptible guys. They are not infected. Now it is uncertain who is getting infection from me
Okay.
and who is not.
So what type of uncertainty? There are thousands of other uncertainty. There is a categories of uncertainty. So what type of uncertainty is this? So what he's saying is the chances of person getting infection. This uncertainty is originated due to what? And each of the reason I'm coming to the point that each different type of uncertainty is modeled mathematically in a different way. That is what I am trying to come. So if you can pinpoint where is the origin of this uncertainty, then you will know which model to use. Otherwise, you are always thinking it's something with the data. What is that data? What uncertainty we are doing?
In this case, it's quite possible that it has not been reported. I am infected, I am passing it to others, but I am not going to the hospital or any medical person.
Okay.
The
So
case will not be reported.
right. So it is underreported or unreported. In that case, the uncertainty is due to underreporting. Underreporting is causing. What other things can be? Yeah.
So in general, when we define something on the basis of something, there are other factors which are influencing, which are not in our prevalence. These cause uncertainty or things.
Yeah. Well, but that is, you are saying, I don't want to worry about uncertainty and I'm clubbing everything together. That's not the way a statistician thinks. That's what I'm trying to come to the point. A statistician doesn't think this way. You are saying, oh, there is something I don't know, and therefore all of those things I club it together. And that's my uncertainty. It is done very separately. They separate it, tease it out, every source of uncertainty. And I'll come to this point that Sir was talking about. That uncertainty source, it could be that reporting error, right? So that means the patients may not be coming to the hospitals. That person was infected, but did not showed up in the hospital. That's a source of an uncertainty, not showing up. Other is person has symptoms, come to the reporting, get reported, but someone noting down made a mistake. Right? Third type of uncertainty is someone noting down but think, oh, he's from this region. He cannot have that type of infection. So he did a bias, personal bias. You see how different uncertainties are there? And these are very much treated very differently by statisticians. It's not like if you go deep into that, you will realize how critical these uncertainties are. And each one has a different modeling implications down the line. How you assume certain things impact your output drastically. And that's why there is a field called as statistics. Otherwise there won't be any things. What they do is capture different type of uncertainty in the empiric data, basically. That's the field called statistics. I don't know if you guys have realized that. So this is what I am trying to, and she is a statistician. So I want you guys to ask that question if something is not clear and go deep into that. She did touch many different things with a very simple way. And I think there were a lot of loaded things in that that information. So Dr. Ghosh, you are still there? Right. Can you hear me?
Yeah, sure. Thank you. Thank you.
Yeah.
Yeah, I can hear you. Yeah.
So,
Thank
where
you,
is
Dr. Mobile, for your nice explanation.
exploring, EDA, where do we use EDA? Have anyone used EDA? For what?
Before developing model, when we get data, we for defining clues which can be included in the model. We many types of examination we do on the data. Scatter plot, we see what of the area, which type of history we are getting.
So exploratory.
We can actually plot the data, and sometimes we can look for the pattern. What kind of function can we fit to that particular data set?
Yeah, so it's exploring the raw data without without going into sophisticated modeling. You're not. Why do we? What is the purpose of the model? What is the purpose of the model?
Good prediction.
Well, prediction actually was one of the worst one to think about from the model, because it doesn't do a good job. Model.
Best fit modeling. And
well, there is a multiple purpose. It's some of the things that they are mentioning is, of course, forecasting. The reason you do modeling is because something you don't know about. That's the reason you do it. If you know from the data, you will not do modeling. You will take information directly from the data. The reason you are doing modeling is you are given a situation, you are capturing it with the models and using that information to answer something else which you don't know. That's the whole idea. It could be future in time, it could be different population. For example, they have studied the behavior of drugs, certain drug for the disease in India, but they don't know what happened in US. So you are using a model for that drug and applying it in US. So taking same time, it's not future time that I'm talking about, but same time, different population. Sometimes we don't know what is the mechanism in which the certain ecological factors are impacting the spread. Why is the disease spreading in this population? I want to know. There are 10 factors. I want to rank them. Number one, is this one very important? See, most of the public policies lacks money. Or in fact, there's no organization with infinite amount of money except Bill and Melinda Gates Foundation. That's a different issue. But most of organizations lack resources or limited resources. So you have to distribute those resources into factors which are key as factors, right? So what is modeling doing is listing out the ranking of the factors. Number one, this is the key factor. This is the less important factor. This is the least important factor. Does that make sense? That's the purpose of the modeling. So actually most of the time this is what it is used for. Not for prediction, not for other population. It is used for understanding which factors we can rank it number one these ways. All these modeling studies are doing that. Okay. Sometimes we don't know, for example, during COVID, we didn't know how many cases are getting infected in Uttarakhand, in Uttar Pradesh, in Delhi. Different types of population, different type of weather condition, different type of pathogens transmission processes. So how will I know? So we were estimating the reproduction number for UP, Uttarakhand separately. And that was giving, it was very fast in Delhi because of factors local to Delhi. And those factors we were listing out. Same thing in UP, same thing in Uttarakhand. It will not be same thing that we studied it in Uttarakhand and it will be in whole India, it will work like that. It will not work like that. So what I'm trying to help you guys with is ask your questions in, it could be very crude question, which is fine. But when you start having discussion, then you realize that there is other aspects that we are not really pondering upon. Okay, so what I will do is I will let her continue and then ask your questions. It is not that simple that, also don't, as I was started the first day, when I was in graduate school, I also had the similar things. What I thought was, oh, this is biology. Why should I listen completely in terms of, this is not my area. But when you start listening to these biologists or to statisticians, your mind try to understand their thinking process. It's very different. As I was saying, the world model in engineering is a toy caricature of some building, for example. Whereas in the social science, it is a flow chart. It's a language is very different. Same word, very different understanding. Mathematics, it's equations, right? Biology is a rat, mouse. So I think we need to understand this language of the field if we want to work in an interdisciplinary area. Otherwise, we are not justifying our research properly. And so that's why I'm saying, statistics, we need to understand what language she's trying to explain it to us. So help us make it more interactive and discussion oriented rather than as a lecture and listening it. Okay? So, okay. So Dr. Ghosh, floor is all yours. So continue please.
Yeah, thank you, Dr. Moy, for your nice explanation about uncertainty and EDA. I continue with some common issues that can affect the explanatory data analysis in EDA. So first of all, there is if the limited data resolution. What it means? Means limited data resolutions happens when the data is too aggregated or incomplete or imprecise to reveal detailed pattern. Why it's problem? Because EDA relies on patterns, trends and variability. If the data lacks details, important information can be hidden. Let's give an example. Like time resolution, data recorded monthly instead of daily. So it can hide the short-term spikes or drops. Another example is like measurement precision. This is one of the most important in different fields like nutritional science or any epidemiological field, like the measurement of age or age group, the co-founder. Age group may be taken as 0 to 18, 19 to 35, 36 to 30 instead of the exact age. So it can be one of the main cause and it is included in limited data resolution. Maybe there is some rounding or truncation errors, that is value rounded to whole number, remove small but meaningful differences. So these types of error or these types of common issues can happen in EDA. Next one is one of the most important is strong assumptions in EDA. So what is strong assumption is? Strong assumption occur when you implicitly believe something about the data without solid evidence. Like already Dr. Mubay mentioned, like particular region. We know this disease was occurred previously in particular this region, but we don't have any idea about any other region have this disease or not. So this is the solid evidence. Is there any disease or is there any particular disease in this region or not? We do not, if we do not have any solid evidence, So we just assume maybe this disease also can incline or decline particular this region. This also may be occurred, and this is one of the issue. So the common assumption, what are the common assumption? We just assume. First one is data is representative, assuming the data set reflects the whole population. But sometimes actually in real field it does not happen all the time. No missing data bias, assuming missing values are random, but sometimes it's not random. We for our easy calculation or easy interpretation, we just assuming the linearity, but it also does not happen all the time. Independent, assuming data points don't influence each other, like particular any disease like tuberculosis does not affect immune system or any other effect, or if we consider like different types of like malnutrition or any or in case of anemia, maybe it's mother anemia or any sanitation, or it does not affect the children's anemia, but anemia and mother's anemia and sanitation or wealth index may be correlated to each other. Stationary, assuming pattern don't change over time. It's sometimes assumed that the pattern does not change over time, but it does not really occur in all cases. Let's give an example. Assuming survey responses represent everyone, even if only a small group responded. So maybe a particular a very small group, due to costing reason, we just collect the response from the small group and assuming the whole response may be same, but it can't be happen all the time. Treating correlation found in EDA as evidence of causation. Assuming normal distribution without testing or visual confirmation. It is generally happen, especially since many of the distribution for large population, we assume it's behave like normal distribution, but maybe it's not only the normal distribution. Impact on EDA means, so what is the impact of strong assumption? So it can mislead the interpretation, overconfidence in early findings, incorrect conclusion that affect later modeling or decisions. Why it's matter? It's matter to generate the hypothesis, not confirm them. Limited resolution or strong assumption can hide real world complexity. It can also like what the actual situation and what the calculation, like what can we interpret. So there is a big difference. Lead to biased insights, already Dr. Mobile mentioned what kind of bias. Affect the variability or later statistical or machine learning models. It can also the model and what we assume, our assumption may be wrong. So there are some techniques to reduce these issues, like multiple visualization. In statistics, there are lots of different types of graph interpolation, like histogram, box plot, or scatter plot, or we can interpret it in different graphs and we can see the pattern, like how it changes or what is the trend of it. Clearly state the assumption when presenting finding, and the one of the reduce these issues. Check the data collection method and the tentative and the final conclusion. Next is correlated parameters. What it means? It means that correlated parameters or variables are the variables that show a statistical relationship with each other. Maybe they are correlated to each other. We need to check it out. When two or more predictors move together, they are not independent. Like give an example, advertising spent across different channels, or temperature or energy usage, height, weight. This is the basic idea of common. Very simple example is height, weight. Of course, height and weight are correlated to each other. So why it matters in EDA? EDA often reveals
Okay, good.
Yeah.
Is your
Yeah,
slide
sure.
moving? What we are seeing right now is your, this is the camera, right?
Yeah, it's just the second point. It's correlated parameter, the third one,
Okay.
the third ball actually, blue
The
ball.
correct slide. Okay, fine.
Yeah. And based on these issues caused by correlated parameters, maybe they can correlate it to each other. It can misleading the interpretation. So in that case, consider this and this point. Next, last we can compare the model. The last point is, so what is the purpose of the model? Model comparison helps decide which model explain the data best while avoiding unnecessary complexity, especially the important when predictors are correlated, or we have any strong assumption or limited data resolution. So in statistics and mechanistic model, here are some points. We discussed with uncertainty matters in public health. Now this is the all possible details. First one is parameter estimation versus calibration. So what is parameter estimation? Parameter estimation basically use data to statistically estimate model parameter with uncertainty. So we guess about, or in statistical language, the guess term is denoted as estimate. We estimate the model parameter. Whereas the calibration is adjust parameters so the model output matches observed data patterns. So here is the basic difference between parameter estimation and calibration. Next one is statistical and mechanistic uncertainty. In statistical uncertainty, what happens comes to the limited or noisy data. But in mechanistic uncertainty, it comes from assumption that I already mentioned in my previous slide. Come from assumption in the model structure. Next one is different parameter and similar curves. Different parameter values can produce very similar epidemic curves, but a good fit does not guarantee correct mechanism. If your model or your curve may be good fitted, but it does not imply or does not guarantee its correct mechanism. Why sensitivity analysis is essential in this field? Like it can measure, check how results change when the parameter vary. Maybe the parameter vary. Maybe we can add or subtract any parameter. So how it vary, how it affect to the result, how result changes. Identify which parameters strongly influence outcome and improves the confidence in conclusion. Like sensitivity analysis is one of the most important cases where we can measure the result changes due to the varying the parameter or identifying which parameter actually the effect, that means the potential parameter, and improve the confidence in conclusion. Like you can conclude what is important and which parameter we can add or we can subtract, or we can, in that case, if we consider the right or potential parameter, we can conclude exactly what happens in the real situation. This is some R code actually. This is actually R. What is R? R is an software generally used in statistics and in different fields. But R is very easy and it is free software, so anyone can use it, and no need to remember the what is the code. You can easily give an access of R, and you can easily remember the code from website or any website. Like here as an example, this is the plot, first one. Plot means the x-axis is based on, first one is based on time, that is put on x-axis, and second one is case, so the case over the time. Next one is if there is any needed like filter, if there is missing data or anything not applicable data, so we can replicate the data with like not available or missing. So in that cases we just easily interpreted by the R code. And last one is this is a simple generalized linear model. The code is GLM. We can easily get from the net. So here this is just an example. Infected means infected people, that varies. Infected, this is Y, varies x1 plus x2, where x1 is age and x2 is any kind of exposure. So we consider it the family as binomial. Maybe it's binomial, maybe it's quasi-binomial. Depends on your assumption and what your analysis, what do you want from your research. So this is the code. Code supports understanding, not blind fitting. So if we fit different types of model, we can also use different types of comparison, like which model fitted well. So this is simple R code. We can easily compare, or we have already mentioned that the graphical visualization. We can easily just input the data into R, and the appropriate code can provide the visualization of the graph, and we can easily interpret it from that. Is it normal or not non-normal, or is inclined or declined, or any outliers? We can easily interpret it. So these are the whole basic about the statistics method, about the uncertainty, why we use it, how should we use it in data, what challenges we face, and that's all. Thank you everyone.
Thank you. Thank you, Dr. Ghosh. This was very helpful, and I'm not sure if you can see the audience. You can now.
Yeah, I can see the audience.
Yeah, so there are a few questions, if it is okay with you.
Yeah, sure.
Please.
Dr. Ghosh,
Yeah.
actually you talk about the strong assumption while doing the data modeling. Like you talk about normality condition. So what do you suggest? Suppose I have a data, especially in disease modeling, I'm not sure what is the pattern and what should be done with the data. So should I check the normality first? Some tests should I apply, because you're talking about the linear regression model, you're talking about parameter estimation. All these are based on the concept of normality. What I understood. So should we check first
Right.
whether data is normal or not, and then we proceed further? And if data is not
Actually,
normal, then
it's
how do we do these parameter estimation?
okay. So actually, in research paper, actually the parameter we can choose the parameter from the literature review, and also in fitting model, actually it's better to. I have already mentioned that it is a good question. So how we choose the model or what we do with the data. So first we is there any visualization of the any graph pattern? You can visualize it's normal or not. It is very easy. And for choosing the model, you need to do what is the research question. You want to calculate the prevalence or any incidence or any exposure which are like influence the disease or anything else. So it depends on your research question. What is the research question? So what we what you want to conclude. So based on this, we fit the model. So the model actually from data then model, not model then data.
Also,
So is it clear?
yeah, I want to add a few things. We are
Yeah, sure.
loosely using word model here. We are trying. Let me just explain very clearly. There is a deterministic mathematical model, and then you need an estimates of the parameters like transmission rate, recovery rate, all those things. Then you build statistical models connecting data to obtain an estimate of this transmission rates, let's say. So this is two different models we are talking about. Always whenever we deal with a data set, you generate a statistical model. The mathematical model is there already. Eventually the outcome of the statistical model will go as an input to the mathematical model. Does that make sense? So for example, transmission rate, recovery rate, for example. How do you obtain a recovery rate? How do you obtain a recovery rate? Which data is needed if I want to know what is the rate at which population people are recovering from a particular disease? What data do I need? Record people of what? Yeah, we will ask the people, or we will follow up that infected people for the duration, right? Duration of infectionness. Usually it is done in two ways. If it is a disease that is not needed hospitalization, even if it is needed hospitalization, people don't show up for hospitalization right the day they are getting infected. Usually it takes few days for them to show up for the symptoms, right? So if I want to know how long a person is infectious or infected, then there is two ways. You will ask a survey to a question. How long do you have for symptoms? The doctor asks this thing, right? And they note it down. And that is called as an electronic health record. That is what on the last day there will be a class on electronic medical records. And that information along with another survey which tracks, because person will show up today, right? They're showing symptoms. Already few days has elapsed. So there is a survey right that day when a person is entering the hospital, and then how many days a person remain in the hospital. So it's an addition of these two terms, two durations. That's the time a person is infected, right? And that time is duration of infected. 1 over that, 1 divided by that duration is a rate of recovery for that disease, that population that we have. Now again, this is one person I am talking about. You have to average it out over many populations, right? Many individuals in the population, right? So you have to think about when we are interested in, see, the actual, if you have a lot of data and you want to extract information from the data, then you test different type of exploratory data analysis. You do normalization, whether the data variables are normals or not. There are different type of analysis you do. But here the question is different. Here the question is, you want to estimate the parameters of the mathematical model and you are using indirect data. For example, transmission rate, as I said earlier, you cannot find it in the field. It's difficult to get it in the, because it requires contact rates. So how do you get it indirectly? How do you get indirectly? By taking the case count data, which is what Dr. Ghosh was talking about, count data, number of cases at different time points. That's a time series data, right? How is this is like this look like scatterplot. And so if I don't know the beta, which is the transmission rate, I give one value of beta, arbitrary value, and then I run the solution of this model and I see how closely it is fitting by taking residuals, right? And we find the residuals. So with that fixed value of beta, there is a certain residual we will get, sum of residuals we will get, right? That's an error. So if I change the beta, there will be a different error, right? So, and so on and so forth. So you will get a list of betas and a different errors, corresponding errors. You find the minimal error and that's corresponding beta is the good fit. And that's how you get. But when you do the fitting, you are using a statistical model in the middle. It's not done, the fitting is a model basically, statistical model. Fitting, fitting can be done in a multiple ways under different assumptions. Now assumption is about what? How the data is collected in the field, how the uncertainty is captured in the field. What data we are talking about? Time series data. Right? This data, how it was collected. That is what as a modeler, statistical modeler has to think about. Mathematical model is done with the model. He's waiting for that estimate to come. You understand my point? So now the question is, you look at this time series data and you do lots of analysis on that. It could be, now it's over time, right? So you have to, it's a count data. I don't know if you have heard about Poisson process. So there's a theory behind it which is based on Poisson process, because it's a count data, counting data, and that's what you use it. And there is assumptions that goes how each of the data points is collected. What is the error for the data collection process made for collecting each of the data points in the time series. So what is the important thing is, how is the fitting model, the statistical fitting model, so there is a hidden statistical model which we don't see. We use these softwares and plug and then we get it. But there is a statistical model and assumptions behind it. That is what we are fitting. You're not fitting the, the mathematical model is getting fit, but there is an intermediate mechanism that is working out as a statistical model. Okay, so that is where is the question is now. If you want to purely do statistical analysis, if I want to only analyze the time series data, it has nothing to do with the mathematical model. We will do a different type of analysis. Right? It's a data, and we want to understand how the cases are changing over time, and we look into statistical models separately. It has nothing to do with the mathematical models. But when we link this data to the mathematical model, there is another type of model which is a statistical model. So these are two different questions. When we ask normality and the data, how to look at the data, we are talking about this part, when you are looking purely statistical aspect and nothing to do with the mathematical model. Even though assumptions are important here also in the statistical model when you fit the mathematical model, but that's a different way of looking and this is a different way of looking. Two distinct things. Okay, does it help like in clarifying?
But we are doing the parameter estimation. Estimation which we do, they are also based on the concept of normality. my data set is not normal, so then the estimation which I'll be getting, then maybe.
But how do you know your data set is not normal?
So that's why I'm asking. That's why I'm asking.
Well, again, when you say data set, what do you mean by data set? That's what I was clarifying. You see, in mathematical model estimation, there are three types of different estimation. One, for example, recovery rate. Did you do any model? No, there was no model. You used the literature, looked for average duration, and you pick that thing up, directly use it. That's a direct estimation from some other study. Second is by you have, for example, raw data and you are averaging it in some sense, weighted average, and getting simple models and then using that thing to estimate your parameter, like adherence rate, for example. Adherence rate in the population, because adherence is to the drugs or to the treatment, to the interventions. Third type of is an indirect estimations, which is basically, as I was describing, the transmission rate is an indirect estimation. You don't have the direct data, you can't average it out something, so it is not possible to get directly from the literature. So you use indirectly time series data, which has nothing to do with the transmission rate, right? Time series is just showing the count of cases. Now in that there is a statistical models. So normality assumptions, you have to look at the time series. At each point is a randomly selected from the population. So each data point has a different assumptions. So there is a normality in each point, not as a one normal, because it's over time. So that's why you have to think about what is the assumption we are talking about here. It's each point that is coming from the data has its own distribution. You understand what I'm trying to say? So it's not one distribution that we are talking about in time series data, it's many distribution. Okay, so there are different assumptions. Again, this is going deep into how we do data analysis before time series data is used in the model. So you want to add, Dr. Ghosh, something to it? Are you there?
Yeah, I'm here. Can you hear me?
Yes, we can hear you.
Yeah. This is your nice explanation. Is there any other question from the
Yeah,
students?
any other questions, guys? Okay, so that reminds me that I will show parameter estimation tomorrow. There will be class in which I will be talking about these things. So that way you will get a better idea of that. But any more issues, questions? How many of you have used a statistical model, any of the statistical model? Yep. And you used it to do what?
Rental estimation in Delhi. We had a data from Kaggle and we did, it is a project, it was a project of the data mining code. So this data, so we first conducted the exploratory data analysis. We get some clues there, like location matches location and distance from important landmarks. And some clusters, so we got some clusters which are dominating the price.
So you had a data.
Data and EDA, we conducted EDA, then we tried to make a model for prediction of the rate at any place in Delhi. We tried, it was not good, but we tried. In that we tried the models like linear regression, then logistic and rich regression, not logistic, rich and lasso. These are the regression models and they not performed very well on the data. Then we moved to ensemble models, decision tree, random forest and another one ensemble model. So random forest was the good for that.
So these are all statistical model that he is talking about. So yeah. So again, for that you need a whole lot of data. right? And in disease models, you don't have typically the data, and that is very challenging. So anyway, so I think Dr. Ghosh, thank you very much. Let's give a round of applause to Dr. Ghosh. Thank you very much, Dr. Ghosh, and hope to see you soon.
Yeah, see you soon. Merry Christmas to everyone. And in the last question, I just need to mention, maybe there is some advanced AI techniques like you mentioned random forest and support vector machine, etc. You can try the cluster analysis if you are interested. This is maybe fuzzy clustering, one of the paper already published. You can use, you can search on net, it's fuzzy clustering. This is based on fuzzy and clustering, based on the cluster data. If the data is clustered, you can use it. This is my suggestion. You can try the model. Okay. Thank you. Thank you again, everyone, and Merry Christmas. Have a good day.
Thank you, Dr. Ghosh. The next thing is we are going for lunch, right? Ashwini, how much time lunch we have?
1 minute.
So no, but how much long break we are taking for lunch? 1 hour? 1 hour is okay? So
In one of the studies
correct.
they've done.
Well, I'm coming to some logical, reasoning with the facts behind it, not the made-up thing. So, basically, the companies are now. I mean, there are lots of open problems. What are the open problems? Not mathematical open problems. Of course, there are many, but there are